In today's lesson, we are going to be talking about stereochemistry. In your previous classes, you would have studied about structure of organic molecules, you would have studied about how to determine the structure of molecules, the empirical formula, the molecular formula, and the physical properties of molecules. You'd have also looked at alkanes and cycloalkanes. You've done something like conformational analysis. And under the alkanes and cycloalkanes, you came across isomerism. Generally, you were told that isomers are molecules that have the same molecular formula but different arrangement of the atoms, or they contain different functional groups, etc., etc. And so at this juncture, you know all about how alkanes are and how they behave, how cycloalkanes are, how their conformations change, and everything. Now, apart from the differences in the connectivity of carbon-carbon skeletons, which give rise to isomers under alkanes and cycloalkanes, which you will look further under other subjects or other topics, there is also stereochemistry. And molecules that are stereo isomers are also another type of isomers, but for these types of molecules, the carbon-carbon connectivity remains the same. They have the same functional group, but the only difference between them is their three-dimensional arrangement, or what we call their arrangement in space. How do I mean by their arrangement in space? It means if you look at the exact arrangement of all the atoms that are involved in that particular molecule in the three-dimensional sense, there are molecules that only differ with the way they are arranged in space, and these are called stereoisomers. And so everything we are going to talk about today from stereochemistry relates to molecules whose difference is only in their three-dimensional arrangement. Only their three-dimensional arrangement. Let me give you a typical example. Look at the molecule 2-butanol. 2-butanol. And I'll draw it simply as this. I'm sure you're all familiar with this kind of nomenclature for organic molecules. Good. I can also draw 2-butanol in a slightly different way, where I put the OH group on one hand and the hydrogen on the other hand. This is just a crude sketch of the mirror images of two molecules. So if I were to place a mirror in here, this line, if it were a mirror, the molecule on the right would look almost as the mirror image of the one on the left. These are not exactly the same. These are just approximations that I'm talking about. Now, on the face value, you realize that if you take molecule A, now let's call this A, and B, if you lift molecule A and you try to put it on molecule B, the methyl group, which is this group will not be able to align with the ethyl group in the B. What it means that no matter how you try, the methyl group and the ethyl group will not be able to align on the same spot. And this is important. We will talk about the importance of such arrangement very soon. And so molecule A and B are said to be stereoisomers. Molecule A and B are said to be stereoisomers. Somebody might ask, why is it necessary to study this kind of phenomena? It turns out that in biological systems, because of the uniqueness of the binding site of enzymes and receptors, they are able to discriminate between molecules A and B as drawn, so that for a particular process, only say molecule B would be able to bind the enzyme or the receptor. And that if it is molecule B that binds the receptor, then molecule A will not be able to bind. And it is because these two molecules differ only with respect to the three-dimensional arrangement of the various atoms that make up the molecule in space. Apart from that, everything else remains the same. So for these molecules, they have similar boiling and melting point. They have the same molecular weight. Most of their physical and chemical properties remain the same, but they differ with respect to the three-dimensional arrangement of the individual atoms and group of atoms in space. Good. So now that we know what stereochemistry is and what we refer to as three-dimensional arrangement and all that, let's go further to interrogate this very point. Now, how come these molecules behave the way they do? If they have the same molecular formula and they have almost the same physicochemical properties, apart from these few distinguishing things that we talked about, then what makes them behave the way they do? Now, if we take the example that we used, which is 2-butanol, let's look at the carbon which I've boldened. That the carbon that has been boldened has this ethyl group. There is the hydroxyl group. There is a hydrogen. And then there is this methyl group. And so if you look at this carbon, all the groups that are attached to it are different. All the groups attached to it are different. And it turns out that it is this difference that gives rise to differences in their geometrical arrangement. And so for molecules that have that contain carbon atoms, sometimes nitrogen, sometimes phosphorus, but mostly we are going to be talking about carbon. So for organic molecules that contain carbon with 4 different groups attached to the carbon, is said to be a chiral center. So if there's a carbon in an organic compound or molecule, and there are 4 different groups that are attached to the same carbon, then that carbon is referred to as a chiral center, and that molecule is said to be chiral. And so 2-butanol will be a chiral molecule, and that carbon 2 will be the chiral center. So it turns out that for chiral molecules, like I mentioned earlier, the 3-dimensional arrangement in space is such that when you have a mirror image of the same molecule, then that molecule would not be superimposable. Will not be superimposable on the mirror image. That molecule will not be superimposable on the mirror image. Let me give you a typical example. If you look at your left and your right hand, your left and your right hand are mirror images of each other. You can take a look at your left and your right hand right now and observe that your left and your right hand are mirror images of each other. But should you lose your hand, your left arm, or your left arm, or your right arm, you can never replace them with the other. So the left and the right arms or hands, the left and the right hands are mirror images of each other, but they are non-superimposable. You can never line your left and your right hand in the same orientation as each other. You can never line your left and your right hands in the same orientation on each other. So we say that the left hand and the right hand are enantiomers. So simply put, enantiomers are mirror images of each other, but they are not superimposable on each other. So they are related by the handedness example. So enantiomers are mirror images of each other, but they are non-superimposable on each other. So they are like the left and the right hand. They are mirror images of each other, but you can't replace one with the other in the same orientation, no matter how you turn them. That's very important concept. enantiomers. Mirror images of each other, but not superimposable on each other. Another concept I want you to understand is what are called diastereomers. These two things go hand in hand. And here we see that enantiomers are mirror images of each other. On the other hand, diastereomers are molecules that are not mirror images of each other. So if two molecules are not enantiomers, then they must be diastereomers. But so stereoisomers that are not mirror images of each other are diastereomers. Stereoisomers first. If they are mirror images of each other, they are enantiomers. But if they are stereoisomers and they are not mirror images of each other, then they are diastereomers. So, important concepts. I have talked about chiral center. I said that the chiral center is the carbon or any carbon in a molecule that has 4 different groups of atoms attached to it. Any carbon in a compound or molecule that has 4 different groups attached to it is called a chiral center. It is synonymously used with the word stereogenic center. They are not exactly the same, but many times you hear people use chiral center and stereogenic center interchangeably. So if a molecule has the chiral center, then it is chiral. If a molecule has a chiral center, then it is chiral. So these are the important concepts that I want you to understand. Like I said, you have enantiomers that are mirror images and diastereomers that are not mirror images, but these are all stereoisomers. These are all stereoisomers and contain a stereogenic or chiral center. In your alkane class, you study that carbon can form 4 bonds. So when you have a carbon, there are 4 bonds that carbon can form. And that you learned about the notation of how to represent these carbon bonds around a 1 or 2 dimensional object. So carbon by itself is flat in a 2-dimensional plane. However, we can represent the 3-dimensional arrangement of the atoms as observed in space. The 4 bonds on carbon are arranged in a tetrahedral manner. So the bonds are arranged at the 4 corners of a tetrahedron. So we say that the sp3 hybridized carbon is tetrahedral shaped. The sp3 carbon is tetrahedral shaped. So one bond will go up. This is an approximate structure for a tetrahedron. And Typically, if you join these ends, then you will see the tetrahedron. But because we're talking about carbon and bonding, we do not use these dotted lines. We just place the groups of atoms or the atoms at the edges of the tetrahedron to depict the structure. You also learn that when you put a tetrahedron on a plane, one of the bonds will point up, and that is represented by the solid wedge. One of the bonds will be pointing away from you, and that is used. We use the broken wedge to represent that bond, whilst two of the bonds will be in the plane, which we use a solid line to represent. So this is a three-dimensional arrangement of the various carbon-containing organic compounds, the tetrahedral arrangement. So if a particular carbon has 4 different groups, let's say X, Y, Z, and W, then this will be the three-dimensional arrangement in space around the carbon. And so if we put a mirror here, we can draw the mirror image of this. Now the Y will be here, the X is going to be there, and then the W is going to be there, whilst the Z is going to be there. Let's say this is A and that is B. These two are mirror images of each other, but again, like we mentioned, molecule A and B cannot be superimposed on each other. What it means is that this carbon with asterisks in both A and B are chiral centers. Now I want you to understand that when we talk about differences, we are talking about differences in molecular weight, okay, or differences of functional groups. Here, functional group is not possible because we are talking about enantiomers, so they should all have the same functional group. But the groups X, Y, Z, and W should have different molecular weights. What it means is that if X, for example, were hydrogen and W were deuterium, okay, these are different. So hydrogen and deuterium are two different elements. Even though they are isotopes, they are also different. So because their molecular weights or atomic weights are different, they are different. And that is how we determine the differences. So we look at the individual groups of atoms and look at the differences in their molecular weights. This molecular weight is important because we use them to distinguish between the various groups that surround the chiral center. Because we use them to distinguish between the various groups that surround the chiral center. So right now, we have looked at enantiomers, we have looked at chirality, we have looked at diastereomers. These are important concepts that I want to remind you as we go along. There is an important feature or parameter that helps us distinguish chiral molecules and enantiomers. For example, we mentioned that if you take enantiomers, they are mirror images of each other, but they are not superimposable. So here, molecule A and B are enantiomers. We also mentioned that for these chiral molecules, for these enantiomers especially, most of their physicochemical properties remain the same. So boiling point or melting point, sometimes density, and all the parameters that we know that relate to the bulk of the substance remains absolutely the same. They are indistinguishable. However, these enantiomers differ with respect to their ability to rotate plane polarized light. I'll take that again. Enantiomers have virtually the same physicochemical properties, except their ability to rotate plane polarized light. So the question is, what is plane polarized light? If you have a light source, that light source produces light in all directions. If I were to put an aperture in front of the light that is able to select just a single plane of the light, that will be a plane polarized light. There are instruments for doing this particular kind of experiment. And in all these instruments, a single plane of the light that is coming through is selected. And the instrument is called polarimeter. So a polarimeter is able to select just a single plane of all the light that is being produced in all directions by choosing just a single directional light. And that allows that light to pass through a sample of the organic molecule or enantiomer that we are looking at. Now it turns out that when you have a plane polarized light going through a solution of an enantiomer, when the light hits the enantiomeric solution, the light is deflected in one of two directions. It will bounce off at an angle, say alpha, from the plane in which it was initially traveling. And that if one enantiomer, deflected the plane polarized light through an angle alpha from its original direction, the other enantiomer will reflect or deflect the light in the opposite direction at the same angle minus alpha. At the same angle minus alpha. So you have the original plane in which the light would have traveled if it were not interrupted by the enantiomeric solution. If one of the enantiomers, like I said, reflects the light through an angle alpha, the other enantiomer will reflect the same light through the opposite angle minus alpha. So the magnitude of the reflection or diffraction remains the same, but the direction remains different. So enantiomers would deflect plane polarized light through an angle alpha or minus alpha. And these are usually measured in degrees. So for molecule A and B, if A deflects plane polarized light through an angle alpha, B would deflect the same light through angle minus alpha. And this is one fundamental difference between these two molecules. And indeed, every other molecule that contains a chiral center. Every other molecule that contains a chiral center. If there's a chiral center, then that molecule would deflect plane polarized light in one direction or the other. And so if you put a polarimeter in front of the sample with a source of light and everything, we will have a certain deflection of the light from an angle alpha or minus alpha for the two enantiomers. This kind of experiment or this kind of behavior is called optical activity. It's called optical activity. What it means is that if a molecule is able to rotate plane polarized light, that molecule is said to be optically active. That molecule is said to be optically active. Optics is for the light, and activity is the ability to deflect. So optically active molecules contain a chiral center and that chiral center is what allows the molecule to be able to deflect plane polarized light. It means the molecule is also chiral. So optically active molecules are also chiral molecules. Let me mention that it is not only chiral compounds that are able to deflect plane polarized light. So optical activity is not necessarily restricted to the traditional chiral center that we know. There are molecules that do not contain a chiral center as we have described, that is, a carbon with 4 different groups attached to it, but they are also chiral. And when you go through your notes, there are several examples of chiral molecules that do not contain a chiral center. A typical example is the molecule that I've drawn here. Just put R prime to distinguish between these two. Say R prime and R. This molecule right here will also deflect plane polarized light, but it doesn't contain the nature of chiral center that we have described in molecule A and B. But for now, that is not where our focus is. There are other examples, like I mentioned, of molecules that do not contain chiral center, but that are optically active. So now that we know that chirality results from having a chiral a carbon with 4 different atoms attached to it, or in special cases where we don't have 4 different atoms, but there are special arrangement of bonds that allows the molecule to be chiral. How do we distinguish between a pair of enantiomers? Because we just said that enantiomers are mirror images of each other, but they are non-superimposable. And since in organic chemistry, naming is important, how do we distinguish between these 2 pairs of molecules that only differ with the way they interact with plane polarized light? How do we distinguish between these molecules whose only difference is between how they interact with plane polarized light? Like we said, one rotates to the left, one rotates to the right. But since these are experimentally determined parameters, we simply cannot look at a molecule and say that it will rotate plane polarized light to the left, or it will rotate plane polarized light to the left or to the right. We simply cannot tell. And so we have to find a way of being able to distinguish between 2 pairs of enantiomers. 2 pairs of enantiomers.